What's the one thing your phone does thousands of times a day that if it were slow would make everything feel broken? It's not checking your messages, it's not updating your apps, it's sorting. And today we're going to dive into the surprisingly awesome quest to make it faster.
I mean, really think about it. You type a single letter and boom, the contact you're looking for is just there. That's not magic. It's the result of a decades-long race to find the absolute best way to turn a total digital mess into perfect, usable order.
So to really get how this all works, let's just picture a simple scenario. Imagine a classroom with 400 students. Every student has a unique ID number, and our only job is to find one specific student using their ID. And believe it or not, that's almost the exact same problem your computer is solving all day long.
To tackle a problem like this, it really helps to split it into two different questions. First, there's the goal, the what. What do we want to do? Easy, find a student. But then there's the method, the how. How do we actually store all that information to make finding someone possible? And as you're about to see, the how changes everything.
Okay, so let's start with the most obvious way. We'll just throw all the students onto one big disorganized list. Now, if we want to find someone, what do we have to do? Well, we have to go down the line one by one. Is this you? Nope. Is this you? Nope. Best case, they're the first person you ask. Worst case, they're the very last one. It works, but man, is it painfully slow.
And that kind of leads us to a huge realization. The real problem isn't the searching, it's the disorganization, it's the chaos. So what if we could fix that? What if our list was perfectly organized by student ID right from the get-go?
With the sorted list, it is a completely different world. Finding the student with the lowest ID? Instant. They're right at the beginning. The highest? At the very end. And finding anyone in the middle? That becomes incredibly fast, with a clever trick where you can eliminate half the list with every single guess. The speed up here isn't just a little better, it's absolutely massive.
So here's the key takeaway. Order creates speed, but we've just solved one problem by creating a brand new one, and this one might be even trickier. We have this giant messy pile of data. How in the world do we efficiently get it into that perfectly sorted list to begin with?
And that brings us to the main event for today, the sorting challenge. This is the big race, the competition to find the fastest, most ingenious way to take a complete jumble of information and turn it into a perfectly organized line. Now you could, theoretically, try let's call it the brute force method. The logic is, well, it's totally bonkers. You basically generate every single possible arrangement of the list, and then you just check them one by one until you find the one that happens to be sorted. Eventually you'll get there. So, why is this a spectacularly bad idea? Because the number of possible orders just explodes. For just 15 students, you'd have to check over 1 trillion combinations. For our classroom of 400, the number of combinations is bigger than the number of atoms in the known universe. So yeah, it's not just impractical, it's physically impossible.
Okay, so clearly that's a dead end. We need a much smarter plan. So let's look at something that's way more intuitive, an approach that's actually kind of how a person might do it. It's called selection sort.
The logic here is really simple. First, you just scan through the entire list and find the student with the highest ID number. Then you take them and swap them to the very end of the list. Great. That last spot is now correct, so we can ignore it. Then you just look at the rest of the list, find the next highest ID, and swap that one into the second to last spot. You just keep doing that until the whole thing's in order.
Now this is a huge improvement, for sure, but it's got a pretty big weakness. See, to place each of our 400 students, we have to scan the list. This is what's called a quadratic time, or n-squared algorithm, and its big problem is scaling. When the list gets bigger, the time it takes doesn't just grow, it explodes. If you double the number of students, it actually takes 4 times as long to sort. This whole scaling problem is what led computer scientists to a really beautiful and powerful idea called divide and conquer. And this strategy is the secret ingredient in one of the most famous sorting algorithms ever created, merge sort. The philosophy behind merge sort is it's brilliant. Sorting one giant list is hard. But what if you had 2 smaller lists that were already sorted? Well, merging them into one big sorted list is actually super easy. So the entire strategy is to just break the big, hard problem down into a ton of tiny, easy problems, and then build the solution back up from there. So here's how it works. First, the algorithm just divides the list in half. Then it divides those halves and keeps on splitting and splitting until it's left with a bunch of tiny little lists that have only one student each. Now, a list with only one item in it is, by definition, already sorted. So now the conquer phase starts. It merges these little sorted lists into slightly bigger sorted lists. Then it merges those, and it just keeps repeating until you have one final, perfectly ordered master list.
That merge step is really the heart of the whole thing. Imagine you've got two sorted lists, and you put one finger at the start of each one. To build your new list, you just compare the two items your fingers are pointing at. Whichever one is smaller, you add it to the new list, and then you just move that one finger forward a spot. You just repeat that. It's incredibly efficient because you never have to go backwards or recheck anything.
In this divide and conquer approach, it's a complete game changer. This is what's known as an n log n time algorithm, and trust me, that is worlds faster than the n squared method we looked at before. Most importantly, it scales beautifully.
So why does any of this actually matter to you? I mean, who cares about all this abstract theory? Well, you do, because this is the reason the technology in your pocket actually feels fast and responsive.
I mean, the difference in performance here is just staggering. Let's say we're sorting 1,000,000 items. That simple n squared algorithm, it would take a massive amount of time. That's that giant bar right there. But an n log n algorithm like merge sort, it's so efficient in comparison that its bar is barely even visible. We're talking about the difference between an operation taking minutes, maybe even hours, versus a fraction of a second.
And that's really the bottom line, isn't it? The difference between a clever algorithm and a basic one is the difference between an app that feels instant and one that's so frustratingly slow you want to throw it against a wall. It is the hidden engine making our entire digital lives possible.
This relentless quest for speed, for the most elegant way to create order from pure digital chaos, is happening constantly, millions of times a second, inside every single device you own. It's the foundation for everything from your social media feed to major scientific research. And it just leaves us with one last thought. What incredible new possibilities are going to be unlocked by the next great algorithmic breakthrough?